So we're going to continue with our discussion on substitution reactions, and this I call setting the scene. So if you watched the previous video, you'll know that the acronym SCENE stands for Sterics, Carbocation, Electrophile, Nucleophile, and the environment. And in this lecture, I really want to focus on the first three letters. They're all interconnected to each other. And so we're going to be looking at Sterics, Carbocation, and Electrophile. Now, all three of these are connected with each other. We are typically, when we are talking about these components in substitution reactions, making a decision here between an SN1 and SN2. These features on the electrophile, the sterics and the carbocation, are all interconnected. So we're going to look at them kind of separately, but they are all interconnected. So let's start off with the first principle, which is that of sterics. And to do that, I want to just look at two very simple examples. What we're looking at over here are two reactions which on the face of it look fairly similar to each other. In both of them we have the same nucleophile, hydroxide, very simple example. And we can clearly pick out that we have a good leaving group on both of them in the form of the iodine. So iodine is a really good leaving group. We'll pull into that information a little bit more just now. But if we look at these, the idea then, of course, is do we get some kind of substitution reaction happening? And it turns out in the very first case over here, we absolutely do. The nucleophile can add to the carbon and the leaving group can go, and we will end up as a product with methanol plus the leaving group that has left the I minus. So that reaction works very nicely. However, it turns out this reaction over here doesn't work at all. In fact, under standard conditions, we really get no product. We don't get the substitution happening at all. And to answer that, we have to understand something about the reaction mechanism, the process of that bond forming and bond breaking, and consider the sterics of what's going on. Now, if you go back to your orbitals, you'll know that when we do this sort of reaction over here, we're breaking a sigma bond. So this is the sigma bond over there. What needs to happen, and so I'm going to bring out a little model over here. Here's my little model of methyl iodide. So we've got the hydrogens, the carbon. So we have this sigma bond over here. Now the sigma bond is the thing that's breaking, but we need to remember that there's also an anti-bond, and that is where the nucleophile needs to engage with. So there's an anti-bond that's sitting over here, and there's an anti-bond that's sitting on that side over there. That's the sigma anti-bonding. And you can go back and refresh your memory about it. When the nucleophile comes in, it needs to overlap with that anti-bonding orbital. So it's going to approach like this from behind over there. It can't come in over here because the anti-bonding is not there and the leaving group is over here. So it can't come in over here. It can't come in over here, there. It has to come in directly opposite the sigma bond. And when it does that, it'll attack there and the leaving group will go. So what we get is a transition state. We can draw it out if we want to like this. So it is difficult to draw it out in 3D, but essentially what happens over here is that these three hydrogens, which were kind of sitting more this way towards us, like that, as the nucleophile comes in, they start to flip around and they go in this direction, so they become coplanar, and then this leaving group, this bond, elongates and goes away. So this is this transition state. It's very high energy. It's almost like carbon has 5 bonds to it, which is impossible, but it's that process of the reaction occurring. And as that occurs over there, the leaving group leaves and the nucleophile comes in. So let's go back to why sterics is important over here. And that is because on this molecule over here, it's really difficult for the nucleophile to get in. So it's helpful if I go and look at a molecule of that. Now have a look at this. This is a really big, clunky molecule. This is tertiary butyl iodide, and it's extremely big. So those are the two equivalents next door to each other. And I think we can appreciate that to get into there is a whole lot easier than to try and get into here over here. There's just a whole lot of steric hindrance over there, which makes it impossible, literally impossible, for a nucleophile to punch in over here to kick out the leaving group. And so a reaction like this via a one-step process, which is SN2, is just simply impossible because of sterics. Now, the rule that we follow here is that tertiary leaving groups, all right, do not undergo SN2. Secondary leaving groups are okay-ish, all right. They're actually quite common, but they are not super fast, whereas a primary leaving group is great. All right. So for substitution reactions, sterics is quite important. One of the first things we need to look at when we're looking at our electrophile is the sterics. And if something is very sterically hindered, so we've got a tertiary leaving group on it, it is almost certainly it's going to have to be SN1. All right. That must be SN1 without a doubt. A secondary leaving group could be both, and that's not that we'd have to look at carefully. We'll deal with a bit more with that. And a primary leaving group is almost certainly going to be an SN2 reaction because it is just there's a lot of space like this over here. There's a lot of space for you to be able to get a nucleophile into. I want to look at the next part of the acronym, which is carbocation. And that is something which we have seen last year, but I just want to remind you about the process. So remember when I said that we're looking at this type of reaction, and so the reaction that we are wanting to look at is an SN1 type reaction. And that is where if this is not going to go via SN2, we need that leaving group to leave like that. And if it does that, what happens is we form a positively charged carbon, and that is our carbocation, which is over there. Now, the first thing that you should actually think about over here when you look at this is that for something like this to happen, must be quite difficult. A carbon that does not have 4 bonds to it is very unstable. And this is really important to realize. This is point number 1 about carbocations. They are very unstable. The second important point, just to keep in the back of our minds, is they are sp2, therefore flat. So those 2 points are really important about carbocations. We're going to look more at their stability now because that's going to help us understand why and when we get them. But the point is, generally speaking, though, we can't just get a bottle of carbocation. It's something that is formed during a reaction. It is very unstable, but we need to understand like what makes it maybe more stable than not compared to other ones. And the other thing just to remember is that they are flat, and this is going to have some consequences, and we'll only deal with that in a later lecture. So, if they're very unstable, are there different degrees of stability? So are there different degrees of stability? And the answer to that is yes. We can look at different stability of carbocations. And the interesting thing is, very simplistically, a tertiary carbocation is a whole lot more stable than a secondary carbocation, which is also a whole lot more, by huge orders of magnitude, more stable than a primary carbocation. So what we're seeing here is that something which has got a primary leaving group on it would make a carbocation that's extremely unstable, and yet something with a primary leaving group on it would typically go via an SN2 reaction like this. We also see that a secondary carbocation is also not super stable, though more stable than a primary. And we can see that it's okay-ish as a substitution, SN2, and it's also okay-ish, not great, for an SN1. But a tertiary carbocation is a whole lot more stable. Let's keep that in context over here. I'm not saying that a carbocation is stable in any way, shape, or form, just that a tertiary one is more stable than the rest. Why is that? The answer comes from something that we've seen before called the inductive effect. So what's going on over here is this carbon that is positively charged over there, very unstable. However, what it does have is got 3 alkyl groups which can very weakly donate electron density towards the carbon center, whereas this one only has 2 and this one over here only has 1. So one of the things that affects the stability of a carbocation is absolutely the inductive effect. And that is why we see that if we've got a tertiary leaving group, we typically go through a carbocation intermediate, and that almost always means that we are going to have an SN1 reaction. We'll deal with that a little bit more. But there is one more thing that will stabilize a positive charge, a carbocation like that. I'm hoping that you've already guessed it. It's my favorite, resonance. Well, the better word, of course, is delocalizations. So this also has a very powerful effect. And so if you get a carbocation that can have some kind of delocalization, it will be a whole lot more stable. So here is an example. It's just a theoretical example at this point. We'll do some practical examples just now. But let's just imagine that we have a leaving group that is actually at this point over here on a primary carbon. Now, we would normally say that this is a really bad thing to happen. So if we take that leaving group and we make it go away, so take its electrons with it, we're going to get a carbocation over there plus our leaving group, which could have been a bromine, an iodine, something, whatever. But now we've got this carbocation. This would normally, we would have said, would have been the equivalent of a primary carbocation. Very, very bad. However, because of the pi bond which is next door to it, that pi bond can delocalize and we can get a resonance form between these two over here. So we can draw just going up. And so we can get a resonance form that looks like that over there. So now we've got a secondary carbocation. So this process here of delocalization stabilizes those positive charges. I want to make a really, really important point right now, and this is so important that you actually just keep this on top of your head over here. Remember that delocalization is not two extremes. We do not have some of this molecule and some of this molecule over here. This over here is showing us a picture. The picture is actually something that looks, I'll just squeeze it in a bit over here. It's a picture where the positive charge is delocalized over that whole system and would look something like that over there. It's somewhere over this whole system, located somewhere between this carbon and somewhere between this carbon over there. And that is delocalization. That's going to be really important when we start looking at products and how these things happen. Okay, so sterics and carbocation of these two things over here are kind of connected to each other. In fact, you might say, well, why do we look at these as two separate things? Well, there are some cases where it would be important to recognize that sometimes, as in this case over here, we might have a leaving group which would initially, you would think, is not sterically hindered, and so it must be SN2 type of reaction because the nucleophile can get in quite easily. But actually, there is a very good chance this is an SN1 reaction because of the stability of the carbocation that comes afterwards. So we do need to look at those two things in conjunction. The last thing that we need to look at is the electrophile itself. And we need to look at that because we need to actually consider what a good leaving group is and how we can affect that in a reaction. All right, so I want us to look at the electrophile part of our substitution reaction. So we're setting the scene, SCE, and the E part means to look at the electrophile. And so we have looked at an example. I'm going to put up the classic example we've done a few times now, which is where we have a leaving group over here like iodine, And so when we look at something like that, and we recognize that this molecule has a leaving group on it, so it is an electrophile. We recognize that the carbon center with the electrophile on it is a tertiary center connected to 3 other carbons. And so when this leaves, it's going to form a tertiary carbocation, which is a very good thing for doing an SN1 type of reaction. And we'll, again, come to the importance of those things through some examples. We also recognize that the carbocation, because of that, is a bit more stable. We've got the steric, so it cannot be an SN2 type reaction. However, what we do need to just pay a little bit of attention to here is our leaving groups. And you should remember that our standard definition of leaving groups is that they are conjugate bases of strong acids. So that is the definition of a good leaving group. And up until now, most of the leaving groups that you looked at have been, of course, the halides, specifically, of course, chlorine, bromine, and iodine. All right, so Cl-, Br-, and I-. Those have been the very good leaving groups. Remember that not F-. Okay, F- is a terrible leaving group because it actually has a very strong bond to carbon, and actually the pKa of HF is about 3. So it's not a strong acid. HF is not a strong acid, so it's not a good leaving group. What we need to look at, though, is there are some other leaving groups that we can have, and to introduce this, I actually want to just look at a particular problem in terms of leaving groups. It's all very well having an iodine there, but the question is, how do we get an iodine there? Say, for instance, and this is one of the most typical problems that we would have. What happens when we've got an alcohol like that? And one of the things is if I want to make that alcohol into, I want that to leave, just like the iodine wants to leave like that. It cannot do it. OH is a terrible leaving group because if it leaves, it's OH-, and that's an absolutely horrendous leaving group. So what can we do to make this into a good leaving group? Well, there are a couple of options that we have available to us. One of the ways is, of course, just to change it into halide. A very good way of doing this is with PBr3, phosphorus tribromide. Phosphorus tribromide is an excellent way to convert any alcohol into a bromine. And so that's an excellent way of converting an OH into a good leaving group. And that's fine. But I want to also introduce some other concepts. One concept that many students want to do, and they want to do it because it's a type of reaction that we're going to see, and that is, but we've got to watch the context over here, is that they want to protonate it. They want to use a strong acid like this to protonate it, to make this into water. So the consequence of that is you get something that looks like this over here. So it's a positively charged hydronium, and that is a good leaving group now at this point over here. But we're going to see that the problem with this is how we get this to react when we've got a nucleophile that's going to come in. Because when we protonate an alcohol, almost always the way this reaction needs to go is via an SN1 reaction. And in this particular case over here, the leaving group is on a primary carbon, and an SN1 reaction is just not going to work. Normally our nucleophile that needs to come in is typically what we're wanting to come in has a lone pair or a negative charge or something, and an acid is just going to protonate that and knock it out of the reaction. So it's going to deactivate the nucleophile. And we'll deal with that in a future lecture. So protonation is one way of making it into a good leaving group, but only under very certain scenarios. There is, though, a very good way that organic chemists use, a very popular way that organic chemists use, and that is to convert the OH into something that we call a tosylate. So I'm going to draw out the product first, discuss it, and then look at how we make those. So we're going to make it into a tosylate. And what we've seen up until now is we've seen this before. We saw TS, in the form of TSO minus. Actually, we saw it in the form of tosic acid. I apologize. We saw it in the form of tosic acid, which was an organic form of sulfuric acid. And the structure of that looked like this. It stood for paratoluene sulfonic acid. And we dealt with that in an earlier lecture. And so this part over here is the TSO part. All right. And this is the acidic H on that molecule over there. All right, so it's an acidic H that is for tosic acid. But tosic acid is a strong acid, and good leaving groups are conjugate bases of strong acids. And so if this is a strong acid, then TSO minus must be a good leaving group. TSO minus. This is a really good leaving group, and one which we use quite a lot. We use it because we can make it so easily from a reagent called tosyl chloride, and we normally just add in a weak base. Triethylamine is something that I've used, but often people will use pyridine as well, just one of those weak amine bases. And this reaction works extremely well. So what it looks like, we can just draw that out. Tosyl chloride, you should be able to work it out from just the abbreviations, but I'll put it in. Looks like that over there. So now we've got a leaving group on there. And actually in this reaction, the oxygen is now the nucleophile. So triethylamine cannot deprotonate that. This is extremely reactive. Very, very good electrophile, very reactive. So the nucleophile adds to the sulfur and kicks out the chlorine. In fact, it's a substitution reaction itself on sulfur. And then in the last step, the base, the triethylamine, can pick up the protons. You can go look at that in your textbook or try and work out the full process of that. But this is an excellent way of changing an OH into a good leaving group. There is a slight variation on this one as well, which we also need to know in this course. It's not just the tosylate that's important, but one that's called a mesylate, which is OMS. So this is now called a mesylate. And it's the me part is because it's a methane sulfonic acid. So what it looks like is just a methyl group with the sulfur and the O minus on it over there. So that's the mesylate. If it was protonated, it'll be methane sulfonic acid, but this is the whole molecule over there, the mesylate. And we get to make this in exactly the same way. So going from there to there, all you need to do is, it's basically the same thing. It's just now mesyl chloride plus triethyl amine as a base over there. All right, so in setting the scene of these reactions, we've been looking at the first three aspects of sterics, the carbocation that is formed, and the electrophile, or really kind of the nature of the leaving group that is on the electrophile. Now there's still more to do. In the next lecture we're going to look at the nucleophile and the environment, but just by way of kind of showing you where we're going with this is to kind of look at two reactions and then decide whether we're going to be doing a SN1 reaction or an SN2 reaction. So let me just use this rather crazy example I seem to always be using with the tertiary butyl iodide, and I'm just going to have ethanol as the nucleophile. There's still more that we need to say about this reaction, but we can certainly identify a nucleophile and a leading group over here. And the product of this reaction would be this. There's still a lot more that we need to cover in terms of just dealing with the other things, deciding between an SN1 and an SN2. But at this point, I just want to show you why we're looking at this. If we look at this reaction over here, we need to decide for ourselves whether it's going to be SN1 and SN2. Part of that is because it's going to depend a lot in terms of like the reaction conditions and things that need to go on in order for this reaction to work. So our starting point is just to identify, when we're looking at the first three are all to do with the electrophile. So sterics, carbocation, and the electrophile need to be looked together. So we look at the sterics, and we see that this leaving group is on a tertiary carbon. And without a doubt, that has to promote SN1, almost exclusively. This is not going to be an SN2 at all. Then we look at the carbocation. If this leaving group leaves, we get a tertiary carbocation, which we've learned is very stable. So this is a good one. We're definitely promoting an SN1 type of reaction. And in terms of the electrophile, the leaving group over here is a good leaving group, but it's a good leaving group for both things over here. So really, these two are really what we're talking about with the electrophile over there. But we're going to see that sometimes when we have a really bad electrophile, it may actually be promoting an SN1. But iodine is a good electrophile. And so we can look at it from those two sides over there and say that actually both SN1 and SN2 are both equally likely. Overall, though, this reaction is definitely looking towards an SN1 reaction and not an SN2. Over there. Let's look at an example which is a little bit more complicated, and I kind of hinted at it when I showed an example. I said, let's take this thing over here, which has a leaving group on it over there, and let's just use our ethanol again, and what we hope that will form would be something like this, OET plus HBr. If we look at this reaction over here and now decide whether it's going to be SN1 or SN2, things become a little bit more complicated. So the electrophile in both cases is the same and same as and should be no problem. Here, the leaving group is a primary leaving group, and so SN2 is also starting to look quite good, but here we recognize that the carbocation can also be stabilized by resonance and delocalization of this pi bond. And so actually, in this case over here, we're sitting between the two in terms of saying whether it's an SN1 or SN2 reaction. And in terms of sterics, this one over here looks totally like it's going to be SN2. And so this reaction over here starts to look a lot more like it's going to be an SN2 reaction, where the nucleophile just adds in and kicks out the bromine. It turns out, though, that this reaction is almost more likely to be an SN1 reaction. And the problem why you can't actually figure that out yet is because we still need to finish working out the difference between the sterics, the carbocation, electrophile, and then the next two components, which is the nucleophile, and something which we haven't got yet, which is the environment. So that's the topic of the next lecture.